Okay, welcome back Science 30s to our next lesson in chemistry. Today we're going to look at 1.2, which is talking about solutions. To start this lesson, I want you to consider what it would be like to fall into the following things. How about falling into a bed? Okay, now imagine falling into a fire. Now next falling into a pool. And lastly, slipping and falling on an icy sidewalk. We can probably imagine what these experiences are going to be like. The bed would be soft and comfortable. The fire would likely burn you and lead to severe injury. The pool wouldn't be quite as soft as the bed, but not too bad of experience. And landing on the hard concrete would probably cause some injury as well, as it would hurt a lot hitting that hard surface. Next, I want you to consider what would your experience be like if you drank these. We have this glass here, this glass there, or this container here. Now, compared to the previous images, this one is a lot more difficult to tell what that experience would be like. The last one, we could tell what the experience would be like based off its physical features, but these all look pretty much the same. They all appear to be clear fluids, and they all do have water in them, but some of them have things dissolved in the water. The first one is just a glass of water. The second one is a drink that has vodka. And the last one is hydrochloric acid. So you would have very different experiences drinking all three of those because of what is mixed into the water and what we call what is dissolved into the water. So in this lesson, we're going to look at when we dissolve things, what that is, and how to measure how much. Okay, we're first going to start with what is dissolving. And we're going to use a really common example of something that dissolves, which is NaCl, which is table salt. So this is an ionic compound, so I'm going to show it going into the water, and that it's made of Na plus and Cl minus ions. This is an ionic compound, those charges are holding it together. Now in the water, what water is H2O, so we have molecules that look like this. We have the oxygen, which is the lighter circle, and then two hydrogens and an oxygen. Now it's a molecular compound, and we talked about this before about sharing electrons, but they don't share evenly. So there will be a plus side and a minus side. We normally write these as partially positive and partially negative, but just for simplicity, we'll put plus and minus. And there's lots of water molecules, so I'll put 2 there. And there's lots of salt molecules as well, or NaCl. They form a big crystal of lots of pluses and minuses, but again, just for simplicity, we have that one Na plus, Cl minus. Now, what I want to show is how these charges are going to interact. So I'm going to take that first water molecule, and it's got that plus on the bottom, and that plus is going to go over to that minus of Cl minus. Then the water over here, I'm going to take the negative there, that is going to move up to the Na plus and grab on there. Now if we have enough water molecules grabbing on, they're going to pull on this bond and be able to pull this ionic compound apart into its individual ions. This is what dissolving is. And when this happens, you can no longer see the salt in the water, because being ripped into its tiniest little ions, which are extremely small, are things that we can't see. So even one salt crystal has lots and lots of Na pluses bonded together. But breaking into its tiny little ions, and we can no longer see it. It's mixed in to those water molecules. So that's what dissolving is. Next, we'll just look at some rules for what dissolves in what, because you may have had the experience where some things dissolve in water and some things don't. So like we saw in the last slide, that this has to do with charges, what can grab on and pull apart. So I like to summarize it in charged dissolves charged. So that means that ionic compounds and polar things are going to be able to dissolve in each other because it's got those pluses and minuses that can grab on and rip it apart. So we saw salt in polar water dissolves. Now this doesn't mean they all dissolve to the same extent. All ionics will dissolve at least a little bit, but remember there was a solubility chart from Science 10 that told you how much it was going to dissolve. And that's kind of what we're looking at in the second part of this lesson, is how much is going to be dissolved in a solution. Okay? Now where we determine if it's going to dissolve a lot or a little is on a solubility chart in your data booklet. It has an AQ and an S, which I'll point out on the side of the chart. So there's your chart, and how we're going to look up something for it's going to dissolve is first start with the negative ion or the anion. So we see Cl up at the top there if I was going to try and determine if NaCl dissolves. So I look at that column, and what that means is for Cl, The first row right here says things that will dissolve well. You can see on that side it's got the AQ below and says that it has a high solubility. But lower down here, it has the solid and it says these things when they bond with Cl have a low solubility. So you're going to see if it fits in the upper or the lower row. Now, the first row here just says most, and it seems like, well, what am I supposed to do with that? That means all of the positive anions that it bonds to except the ones that are down here. So this says when Cl minus is bonded to pretty much anything that is plus, except for these pluses down here, it's going to dissolve well. So everything except these ones are going to dissolve well. So what doesn't dissolve well? We can see Cu, Ag, Pb, and Ti. Those don't dissolve well with Cl, everything else does. Okay, so just put some colors on here. These all dissolve well, these all dissolve poorly, and that's how we read that chart. The next rule for solubility is that non-charged dissolves non-charged. So charges were dissolving charges, and now we can see that non-charged dissolves non-charged things. So if you had a solution of a non-charged chemical, something that was just molecular, and you were dissolving something molecular, that should dissolve. So basically molecular compounds dissolve molecular compounds, again, that aren't polar. And the last part is that charged and non-charged don't mix. So sometimes it's summarized as like dissolves like. So charges dissolve each other, non-charges dissolves non-charged, but if you mix the two, you get an example like this, where you can see oil and water. Oil does not have any charges, and then water is polar. It's got those partial charges. And you can stir them up as much as you want, they just don't mix. So now that we've covered what dissolving is and the rules for what dissolves and what, let's take a look at measuring how much is going to be dissolved in a solution by looking at moles and molar concentration. Okay, so a mole is just a group of stuff, but it's such a big group that I think sometimes it's hard to lose perspective for what it is and how to do these molar concentrations. So to kind of relate it to another group that we're familiar with, I'm going to relate this to a dozen. Okay, so we're going to have a dozen over there and compare it to an example looking at a mole. Both are just groups. A dozen means 12 of something, and we could have 12 donuts, for example. That would be 1 dozen of donuts, as if we had 12 of them. And a mole is, again, just a group, but it's a much bigger number. 6.02 times 10 to the 23. That's a really big number, but you need a really big number to make it so you can see the amount of atoms because they're so small. So a mole of carbon atoms looks approximately like that. You can see the scale weighing out the correct mass of 1 mole, which we'll get to in a moment. So I want you to think just a group of stuff. So now let's see if we can apply mole questions with using the analogy of dozens and see if we can take that relatively simple math and apply it to what seems more complicated with a group of moles. So the first question that I've put up here is a dozen mass, or meaning the mass of a dozen chocolate donuts, is 456 grams per dozen. You have a box of a dozen donuts, it's 256 grams. Now if we look at atoms, we look at the mass for that many carbon atoms. So it says the molar mass, the mass of 1 mole of carbon atoms, is 12.01 grams per mole. Okay, so we have grams per dozen and grams per mole. How could we apply this to some questions? Let's say you had 1,360 grams of chocolate donuts. How many dozen do you have? I'm going to think, okay, I'm going to take all the mass that I have and divide that by the mass of a dozen. So I go 1,368 divided by 456, because that's the mass of 1 dozen, and I get that that would be 3 dozen donuts. Okay? If we apply the same to atoms, we said we have 48.044 grams of carbon. How many moles is this? Well, I know 1 mole is 12.01, so let's divide by that, and I can see that I have 4 moles of carbon atoms. Okay, let's do one more example. Put those away. How much does 2.5 dozens of donuts weigh? Well, if we know 1 dozen is 456, we just times that by 2.5. So 2.5 times 456, and we got 1,140. Similarly, if we're looking at atoms, how much does 1.8 moles of carbon weigh? I go 1.8 times the mass of 1 mole, and I get 21.6 grams. Those are the calculations that we look at often for determining moles or determining mass that we'll see with the formula on the next slide. So now putting that a bit more formally into our notes, this is the formula for all those mathematical processes we were doing before. So it's N is equal to little m over big M. And the N stands for the number of moles, the little m stands for mass, and the big M stands for molar mass. Okay, so that's what we used in the last example. They're just rearrangements of that. So if you wanted to find the amount of mass on top, you'd multiply the big M to the side. So number of moles times molar mass give you moles. Okay, so it's just rearrangements for that formula. Again, hopefully that one's familiar from earlier science courses. The new thing we're going to look at is molar concentration. This is our new formula. So this describes how many moles of a chemical is going to be dissolved in a solution. It's written as moles per liter, or sometimes just with a capital M and said as molar. So if you had 2 moles per liter, you could also just say 2 molar. Now the formula is not too complicated. It's just C is equal to N over V, so just a 3-variable equation. Our C stands for the molar concentration. The N, same as the N from the last one, number of moles, and the V is going to be the volume. Make sure we measure that in liters. So now let's take that recap of moles and what we learned new about molar concentration to do an example like this. If 100 grams of copper 2 sulfate is dissolved to make a 400 milliliter solution, what is the molar concentration? Okay, first step will be to find moles, next will be molar concentration. So I set up my first formula there, N is equal to little m over big M. Fill in that I know I have 100 grams, but I want to figure out how many moles this is. So I have to divide by the molar mass. To determine the molar mass, it's on the periodic table. It says how much each element is going to have in grams per mole. So we have the formula CuSO4. Now it's really important that we start with the correct formula, because if you don't start with the correct formula, you're not going to get the correct molar mass, which is going to affect the rest of the calculation. So make sure you balance this out. Copper 2 means copper 2 plus, sulfate, that's SO4, 2 minus. So 2 plus, 2 minus, we're balanced there. If it wasn't balanced and we had to increase the amount of copper or sulfur, we have to increase the mass because we have more carbon, sulfur, or oxygen atoms. So really good that we get it balanced off the start. Now that we've checked that it is balanced, we'll put up the masses for each of these. So copper on the periodic table is 63.55, sulfur is 32.07, and oxygen is 16, but we see in the formula that there are 4 of them. So I need to go 16 times 4. We need the mass of all the atoms involved here. So 1 copper, 1 sulfur, 4 oxygens. We add all those up together to get the molar mass. I get 159.62 grams per mole. And that's it for today's lesson. I hope that helped you to understand dissolving and looking at moles and molar concentration. Thank you so much for watching this video, and I will see you in the next lesson.